Okay, welcome back. Hello, I hope you all are well. This is 11.1 Lecture 3, which is going to be our last lecture on Section 11.1. So hopefully this one will be shorter. That's my goal. Maybe that makes you excited. We'll see what happens. This is going to be more on the limit laws, theorems, terminology, evaluation of limits and things, and a little more proof, right? Where would we be without that? Also, make sure you're paying attention to your email, the announcements on Canvas. Every time I send an email, I try to post it also as an announcement. Make sure you're paying attention to those things. I've sent you some emails about some information about Quiz 3 on sections 11.1, 8.1, and 7.8, right? Sequences, arc length, improper integrals. Which will be April 1st, no fooling. So make sure you read that email and get back to me if for some reason you cannot work with the time that I have in that email. So with no further ado, let's continue, right? So what I want to do is look at some of the examples that are both in the book and some of the exercises that you've been assigned for homework, yay! And we're going to look at some ways to solve those problems that might be a little bit different too. So let's look at an alternate solution to example 5 in the book. So example 5 in section 11.1, we've got the limit, you're computing the limit as n goes to infinity of n over the square root of 10 plus n, okay? Now, why are we doing this problem? Well, you know now, right, you're taking a limit of some a sub n, and that means what are you doing? The question really is, right, does the sequence, right, when we draw these curly braces, this is the set containing infinitely many numbers in an ordered list, the sequence, what sequence is it? This guy right here, n over, it's generated by n over the square root of 10 plus n. Does this sequence converge or diverge, right? That's what we're looking for. And so by considering this limit, we're trying to answer this question. Yes? Okay. This guy's our a sub n in this problem. Okay. So now what can we do? Your book does it one way. I'm going to do it a slightly different way. And all of them are valid. This way we'll just highlight a little bit more of one of the limit laws we didn't talk as much about. So here, what we're going to do is instead be like, you know what, this square root here is sort of annoying, right? I wish that square root wasn't there. If it wasn't there, it'd be a lot easier to deal with this fraction, right? And so I can't just erase it, you know, I'm not allowed to do that. But I can rewrite this in a way that will make my life simpler. Your book deals with this problem in a different way. Make sure you understand how the algebra there worked. Okay, make sure you can fill in the missing details. But here's what we're going to do. You know what? I just want there to be a fraction. I don't want the square root to be only with one term. So I want the square root to be with both terms, right? And so if I do that, then I still have a 10 plus n in the denominator. But what am I going to have in the numerator in order that these two things are equivalent? Good. N squared, right? The square root of n squared is n. Ooh, some of you are out there saying, hey, wait, the square root of n squared is the absolute value of n. Very nice, good. But what do we know about n? N is generally starting at 1, n is positive or greater than or equal to 0, so we don't have to worry about that subtlety in these problems here right now, right? So the square root of n squared is n, and the square root of a fraction is the fraction of the square roots. Yes? Algebra. Okay, so now what can I do? So here we're going to highlight one of the other limit laws that are in the box that I told you to pay attention to. Here we can think of this in two different ways. One, this is actually the limit as n goes to infinity of this function to a particular power, right? The power, what is the square root power? Good, 1/2, right? So that's that to the 1/2. And there's a power law, a power rule in there, the last limit law that says the limit of stuff to a power is the power, which is 1/2, our square root, times the limit of the stuff, or evaluated at the limit of the stuff. That's the words we really want, okay? Another limit law is when, if we think about this guy, our outside function as being f, and that being the square root function, and we know that the square root function is continuous at any positive or input or 0 to the right, then we also have the limit law that says if this outside function is continuous, then this limit can just go right inside the outside function to deal with the inside function, and then the result will be figuring out what happens just with this inside guy and then applying the outside function. We love that, right? That was limit laws for composite functions. So this guy is so much easier to deal with. The limit then goes to infinity of n squared over 10 plus n. So let's do that one here off to the side. The limit as n goes to infinity of n squared over 10 plus n. Now again, there's lots of ways you might think to do that. This you might want to try L'Hopital's rule, but again, you really probably don't want to get in the habit of that, even though it does work. And really the better process to go through, which will be a process that will get used over and over again as we move along, will be the idea of taking this limit. This is an infinity over infinity indeterminate form, right? Like we saw one of the last times. And then we divide by the highest power in the denominator. So what is the highest power in the denominator? Good, just n, right? And so we're going to take this limit, right, and we're going to take each of these guys, and maybe I'll just here write in green now. I'm going to divide each guy by n, right? N, 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 right? Divide every term by the highest power in the denominator. And so then what do I get, right? This becomes the limit as n goes to infinity. N squared over n is just n, very nice. 10 over n, n over n is just 1. Yeah, are we good? Okay, and so now what do I have going on here? As I look at this particular limit, 10 over n, what is the limit as n goes to infinity of 10 over n? We've got constant over something growing huge without bound. What is that limit? Is that indeterminate? No, good. What is the limit as n goes to infinity of 10 over n? Good. This guy goes to 0. Constant divided by something getting huge, right, without bound, is going to 0. And so the denominator is going to 1, right? The denominator is going to 1, at 0 plus 1, right? And the numerator, right, is n, and where's n going to infinity, right? Again, we never use equals. I know the book and the WebAssign does, but we never use equals because you never can equal infinity. And so what is this guy doing? That's going off to infinity. It's growing positive without bound, right? Beautiful. So that's what's happening to the inside of this guy. And so what do you know about the range of the square root function as the input grows large without bound? What about the square root function? What's its range? It also goes off to infinity, and so this guy the whole limit is going to infinity. I'm gonna resist. I don't want to write the square root of infinity is infinity, right? We don't want to really talk like that, but we get what we just said, yeah? So this thing is growing without bound. Therefore, which of these two things converge or diverge? Good, diverge. Yeah, okay, awesome. So that's another alternate way of doing example 5, okay? Now let's look at another problem. Okay, yep, you can see my knee keeps getting better and better. His ability to bend down and pick up the things I drop keeps improving. Alrighty, so let's see, what will we do next? Here is a nice theorem, okay? This is a very nice theorem. A very nice theorem. And what does this theorem say? This theorem says, that's not the actual name of it, but it's going to be real nice for us. It says if the limit as n goes to infinity of the absolute value of 8, and I know you guys are like, oh no, not absolute value, but it's okay. This is going to help you. This theorem is going to make you happy, right? If the limit as n goes to infinity of the absolute value of the nth term of a sequence is 0, right, then the limit as n goes to infinity of just the nth term of the sequence has to be 0, okay? So this is the limit of the absolute value theorem, maybe you could call it that. If we know that the limit of the absolute value is 0, it's got to be 0, otherwise none of this is going to work, right? Then I know that the actual guy is 0. Now why is this nice? Because if I take absolute value, then I don't have to worry about any sign changes, any of that weird bouncing back and forth stuff. I can just ignore anything that's negative, make it positive, and if the limit is 0, then the limit of my original guy is 0. So let's look at an example first before we talk about why this theorem is true, okay? Let's look at first an example, and here is, as an example, we're going to do one of your homework problems. Yay! Exercise number 35 in section 11.1. Also a web-assigned problem, or maybe it is a web-assigned problem. So for this problem, we've got a sub n is minus 1 to the n divided by 2 over root n, okay? So this is the problem that we need to worry about, and again we're asking, does this sequence generated by these a sub n's converge or diverge, right? And dealing with that, -1 guy to the n, that might be a little bit annoying, right? So let's look at instead the absolute value of a sub n, okay? What is the absolute value of a sub n? What's the absolute value of this expression, right? Okay? But we saw last time the absolute value, right, of a quotient is the quotient of the absolute values. We know that. The denominator here, 2 is positive, square root of n is positive, so the absolute value of that is 2 times the square root of n. And the numerator we saw very first time, I think, is a guy that bounces back and forth between -1 and 1, right? So absolute value of something that's either -1 or 1 is just 1. Very nice. Okay. And so that, looking at the absolute value actually simplifies things for us, right? So now we only care about, so consider the limit as n goes to infinity of the absolute value of a n, which is the limit as n goes to infinity of our guy right over there, 1 over 2 root n. We just talked about the range of the square root function, right? As n goes to infinity, where is the square root of n going? Great, it's growing unbounded. So 2 times that is growing unbounded, positive, right? And what do we have? Then we've got constant divided by something getting huge. What is that? Good, that limit is 0. Whoa, we're so happy, right? Because 0 is the only thing we can get out and actually apply this theorem, right? So since we've just shown that that limit is 0, therefore, by our awesome theorem, by our nice theorem, we call this one nice theorem, by our nice theorem, then the limit as n goes to infinity of our actual a sub n, which is -1 to the n over 2 root n, is also 0. Yeah? So that's super nice, right? That allows you to avoid having to deal with the moving around of the terms of a sequence. Let's look visually real quick at each one of these guys, right? So if we wanted to look at the absolute value of an, right, and we wanted to look at that sequence, right, here's n, right, when n is 1, right, what do we get, right? So our absolute value of an is this guy, right? We would have had 1 over 2 times the square root of 1, so we get 1/2, right? So we have that dot, right? When n is 2, we get 1 over 2 times the square root of 2, which is smaller. When n is 3, it's 1 over 2 times the square root of 3, which is smaller. When n is 4, it's 1 over 2 times the square root of 4, right? Good, which is 1/4. There we go, right? And so we can see what this sequence is doing, the absolute value of an. It's just going to get smaller and smaller and smaller and converge on 0, right? Eventually, you can always go far enough out in the sequence to be within an epsilon distance of 0, right? Yes? Okay, very nice. Our definition of what that really means with math. Okay, but what about the actual guy that we were looking at of interest in this problem? The actual sequence AN is generated by this formula, right? So here's N, there's AN, here's 1, right? What is A1 for this sequence? That A1 is minus 1 to the 1, which is negative 1, right, over 2 times 1. So negative 1/2 is our first term, right? When N is 2, right, minus 1 squared is positive, so we got 1 over 2 root 2, so now we're back up here. When N is 3, that top guy's going to be negative, so now we're there, right? When N is 4, then we're back at a quarter, right? Because we're here. And then we're going to just kind of straddle, when N is 5, right? We're going to straddle the line AN equals 0. We're going to also converge to 0, but converge to 0 by bouncing back and forth across numbers that alternate positive, negative, but keep getting closer and closer and closer to 0. Even so, there will always be a place where, as long as you're far enough out, no matter how small an epsilon we want to choose away from 0, we can always be within that epsilon band of 0, right? So both limits are 0, right? And there's a visual of what's happening with those sequences. Okay, does that make sense? So try, as you're thinking about these things, not to get lost in the subscripts and the notation. Try to remember what it is, right? It's a bunch of dots, right? It's a bunch of numbers, okay? And you're trying to understand what they're doing, yeah? Okay, and that's going to be important to not mix it up when we move into the next section, all right? Okay. So let's do a proof of this nice theorem, right? Because we've just seen that it's pretty useful. So let's prove this, and it's not a superfluous, however you want to say that, proof, because it's also, the proof is also one of your homework problems, right? So this is another benefit of Math 236 at home edition, right? I'm going to try to do some things that I might otherwise let you struggle with for a while first. All right, so this is exercise number 87, one of your homework problems, and it says prove this nice theorem. Okay, now we could prove this nice theorem in a variety of ways. One way is by going to our epsilon n definitions of what these guys mean and setting up the fact that we know this and we're trying to show that, okay? We're going to do it a slightly different way because it's just super quick and fast, right? And it also will highlight another theorem that we haven't talked about that's a limit theorem in this section as well, okay? And you'll remember this theorem is very similar to one that you saw in Calc 1. So we want to somehow conclude that this guy, a sub n, this limit is 0. And we know that this limit is 0. So who remembers the squeeze theorem from Calc 1, right? You always loved the squeeze theorem. It always seemed like you only used the squeeze theorem when you had a sine or cosine, something crazy in there, right? So here's a nice use of the squeeze theorem, okay? So if we're going to use the squeeze theorem, and you can read it in your textbook for sequences, if we're going to use the squeeze theorem, then the thing that you're trying, like the hard guy, the limit that you're trying to show, that's the guy that's in the middle, right, of the inequality. Remember, the squeeze theorem says if I can trap something between two other things, and then these two things on these ends both go to the same limit, then this guy also has to go to that same limit. No other choice, right? Okay? All right. So I want to try to trap this guy between two things. And the question is, what are those two things, right? Well, you got to use something you know, right? So what's the only thing we actually know in this problem? Our hypothesis is if I know this is true, right? And so compare absolute value of AN in AN. Like, what can you say is going to always have to be true? You know, understanding something about the absolute value of something. Good. the absolute value of something is always bigger than or equal to the thing you're taking the absolute value of, right? Because this guy's always positive, and this guy could be positive or negative, yeah? Okay. Now, what goes on this side? Any ideas? Remember, an could be negative. We only know something about him. I think somebody got it out there, right? The negative of the absolute value is going to be a lot smaller, right? Or going to be smaller than or equal to the thing, right? Yeah. Just think about it like this. If we just use the number 5, right? If an were 5, 5 is less than or equal to the absolute value of 5, which is greater than or equal to minus the absolute value of 5, right? Okay. That's minus 5 is less than or equal to 5, which is less than or equal to 5. Yes? But if an were negative, minus 5 is less than or equal to the absolute value of minus 5, which is greater than or equal to minus the absolute value of minus 5, right? So now if an is negative 5, what's the absolute value of negative 5? 5. 5 is greater than or equal to negative 5, which is greater than or equal to minus 5, right? Both of these two inequalities are true. And that's what this guy's saying. And so this is awesome. We have our inequality for the squeeze theorem, and now what do? We take limit, right? Okay. So we already know for this guy, we're given that the limit as n goes to infinity of the absolute value of a sub n is equal to 0, right? That's by our given. And what about this guy? Well, then we got to do the limit as n goes to infinity of minus the absolute value of an, right? But minus just means the constant minus 1 times this, right? That's the limit of a constant times a function, right? And for sequences, the constant times our term. We have a constant multiple rule for limits as well. The constant comes out, right? The limit of a constant times in Calc 1, a function, is the constant times the limit of the function. It's the same with sequences. So it's minus 1 times the limit as n goes to infinity of the absolute value of an. But what do we know the absolute value of an is? The limit as n goes to infinity of the absolute value of an? We know that limit is 0. So minus 0. What is minus 0? Also 0. So this limit is 0, and that limit is 0. Therefore, by the squeeze theorem, the limit as n goes to infinity, the guy in the middle, right, is squoze, and that limit also has to be 0. So there we have it. Woo. Yeah? That's one that's going to be super useful later as well, okay? So we want to hold on to that in our minds. All right. While we're on a proving, like, you know, we're on the prove groove, right? We're on the prove groove. So let's do one more proof, yeah? Okay? Of yet another concept that's going to keep coming up over and over that we're going to want to make sure we have in our repertoire that we're beginning to build here with chapter 11. All right, you guys know this by now. I'm going to create some more space. Okay, so also one of your homework problems. Here we go. Homework number 86. All right, we're going to prove that the limit as n goes to infinity of r to the n is 0 when the absolute value of r is less than 1. Okay? I think I'm going to get a drink of water first. You can take a breather. We did a problem like this. Really, we're only going to consider r not equal to 0 as well, right? Why? If r were 0, right, then what do we have? The limit as n goes to infinity of 0 to the n, right? 0 is itself, this is just 0, right? It's not something that's tending towards 0, and so that limit is 0, okay? So this guy is just 0, so 0 doesn't matter. Now, what does this mean, right? The absolute value of r is less than 1. That means right? The absolute value of r less than 1 is the same as absolute value notation. If I want to get rid of that, what is that? Good. Minus 1 less than r less than 1. The distance between r and 0 is smaller than 1, right? So we can think of it visually. Here's 0, right? Here's 1. Here's negative 1, right? Okay, so where are we? If we're in there, then we're here to here, right? But we just said we're not going to include 0 either, right? So, so with both of these guys, then we're really just thinking, if we're thinking about an r-axis, then this is what we're thinking, yeah? We're from there to there. Values of r, so r could be a half, r could be 3/7, like the problem that we did the other day, 2 lectures ago, I believe. R could be negative 5/6, right? Okay, and so what we're saying is, right, anytime we have a number that's between negative 1 and 1, right, and we're raising that to the n and taking a limit as n goes to infinity, the limit of that thing is 0. And that seems to make a lot of sense. Again, if you think about the number 1/10 and you keep multiplying it times itself, right, it gets super, super, super small eventually, right? Okay, so let's prove this in general, even though we have some instinct about it, okay? So what would we do? Well, what do we need to do? We need to write down what that means, okay? So in order to prove this, right, so to prove, we need to prove what? We need to prove that for every what, so r is getting, this guy's getting close to an actual limit, so we're measuring a distance here between these two guys, the distance between that and that. We use epsilon for that, right? For every epsilon greater than 0, there exists, now this guy's getting huge, right? So we use n to give us a place beyond which we're getting huge. So for every epsilon greater than 0, there exists an n greater than 0, such that if what is true, little n is big enough, right? Okay, n grows, n is bigger, little n is bigger than any capital N, than that capital N, then what's true? The distance between this guy and this guy is less than epsilon, right? Good. Then the absolute value of r to the n minus 0 is less than epsilon, right? That's what we got to prove. Yeah? Okay. So, again, we could start off our proof, right? We know how this proof's going to start. Just to get rolling a little bit, yeah? We got to respect, right? We got to respect for every epsilon greater than 0, we're like, bring it on, bring it on. What are we going to do? We're going to say, you think that's going to stop me? No way. Let epsilon be any positive number. No problem at all, right? No problem. I can deal with that. Whoops. Then what? Then we deal with this guy. We got to demonstrate the existence of a capital N, right? So we know we're going to have to choose capital N to be something, or let capital N be something. We're not sure what that is right now, so we're just going to leave ourselves a space, okay? Then what? I'll just make use of all these colors here today. Then what? What's the third thing we know, right? We know that this is true because it's the hypothesis in our if-then statement, right? So we get to let that be true as well, right? Let n be greater than capital N, right? And then we have to kind of step our way forward in order to end up with that statement. So that's where we go and try to leave ourselves some breadcrumbs, right? Okay, so here's our breadcrumbs, right? Side work, not part of the proof. We just pretend we never did this when we write up the proof, like we were geniuses and we knew immediately what to call capital N and how to make the bridge. Down to what? What is our very final statement? We can just go ahead and write that in there. What's our very final statement going to be, right? Or eventually our final statement is going to be therefore, right? The absolute value of r sub n minus 0 is less than epsilon. And I've proven it. Yay, right? Okay? We just have to fill in the middle. How are we going to fill in the middle? We're going to lead ourselves there. Okay? So let's look at this expression, right? We've got r to the n minus 0 is less than epsilon in absolute value. That's what we're going to want as our final statement. What would have to come right before that in order to conclude that, right? Well, here we're kind of saying, okay, well, what's, the easiest way to simplify this right now? It's just to say, well, the absolute value of this minus 0 is just the absolute value of that. Yeah, right? We good? Okay, nice. All right. Now what? Remember, right? Can we just drop these absolute values? No, right? We're staring right here. R can be negative, yeah? Okay, and so, but the absolute value of some number to a power is the absolute value of that number to a power, right? Understanding our rules of exponents and absolute values. So we got that. These guys are equivalent, yeah? Okay, and now, right, what was always kind of the goal here, right? We want little n to be bigger than capital N, right? So we kind of need to, we don't know what this guy should be. In order to find it, we need some inequality with little n. So we need to solve this for little n, right? Solve for little n. How am I going to solve this for little n? What can I do? How do I have to get an exponent out? What do I need to use to get an exponent out of get something out of an exponent? Good. Right? I take the natural log of both sides, right? Yes. Okay. The natural log of the absolute value of r to the n, if we do that to this side, we have to do it to this side, is less than the absolute value of epsilon. Now, since the natural log function is a monotonically increasing function, right? Then this is legit to go from here to here. Okay, so now what? Now, what do? What's our favorite natural log property here? Right? Good, that guy goes down, right? Natural log of a to the b is b times the natural log of a. We're also reviewing a bunch of things that will be good to have at our disposal as we move along. Right? So these two guys are algebraically equivalent by the algebra of natural logs. What was our goal again? Solve for n, right? Get something that n is greater than. Now hold on here. If I want to solve this guy for n, I would just divide by the natural log of absolute value of r, right? But that would be n is less than something, and I need n is greater than something. Did we do something wrong here? Did we do something wrong here? Well, let's think about that natural log function for a sec. What does the natural log function look like? If I do natural log of x, right, and this is x, what does natural log look like? Good, there's natural log. What is this number right here? Very nice, 1. Excellent. What can you tell me about the natural log of x for a number between 0 and 1? Yeah, it lives down here, right? It's negative. Good. So if I want the natural log of the absolute value of x, then that's just going to give me another branch over here, right? Where this guy here is negative 1. So what is true about the natural log of something between negative 1 and 1? Not including 0. Good thing we ruled that guy out, right? Because we know natural log of 0 does not exist. Yeah, that would be bad. But between minus 1 and 1 for this set right here, not being 0, this guy is negative, right? So here, natural log, right, of r, of the absolute value of r, is negative. And if I divide this inequality by a negative thing, right, if I divide by that, then I'm just going to have n left over here, and over here I'm going to have natural log of epsilon divided by natural log of the absolute value of r. But if I divide by something negative, what happens to this sign? Woohoo! Yeah, turns to greater than, right? And therefore, what did we just discover? This guy is n. Because we needed little n to be greater than capital N. We didn't know what capital N should be. So now what do? We come in here and pretend we always knew that capital N, as if we were genius, should be the natural log of epsilon divided by the natural log of the absolute value of r, right? Like as if we knew it from the very beginning. And then this is off somewhere, not even part of our proof, right? This is our proof. And now we just pick up with our proof. So let's just go ahead and finish this one out since I made you finish the other one on your own the last time. just so I wouldn't run, well, I guess I never run out of time now, right? But just so the video wouldn't be so long. So anyway, back to here. What do we do now? What's our next step? We know little n is bigger than capital N, right? Here our capital N is a function of epsilon, right? As epsilon changes, n changes. And so we can now just say, well, since n is greater than little capital N, and capital N is that, right? Therefore, little n is greater than the natural log of epsilon divided by the natural log of the absolute value of r, right? Okay? And then what do? We just walk our steps and pick up our breadcrumbs backwards, right? And add a few words, right? Just to be nice and conversive, yeah? Okay. So, here's not a bad idea to say, right? Since, oh, that's another thing we probably should have put in here. Let's just squeeze it in here. Maybe right here. Sorry. Let's squeeze in here. Let the absolute value of r be less than 1, r not equal to 0. Right? Yeah, because that's another condition that we have. So, since the natural log of the absolute value of r is negative, right? That's what we needed. That's what gets us from this step to this step. Yeah? And so, right? Draw that there. Right? We needed that negative to be able to change that sign, right? And so we have, right? Do I have to think? No, I just write that. And natural log of the absolute value of r is less than the natural log of epsilon, then I just keep picking up my breadcrumbs. Therefore, the natural log of the absolute value of r to the n is less than the natural log of epsilon. And so, the absolute value of r to the n is less than epsilon. Really, from here to here, what are we doing? We're taking, we're again using the fact that natural log is monotonic, or really taking the exponential of both sides, right? And using the fact that the exponential function is itself monotonic, increasing as well. Okay, and then we're here, thus, oh, whoops, we left way too much space. Thus what? The absolute value of r to the n is less than epsilon, which is equivalent to, here, our guy, I guess we don't need the therefore if we write that, which is equivalent to that, which we prove now, our guy. Woohoo! Yay! If you're a little wigged out by the r, try it for yourself. Try for yourself. With, say, r equals negative 3/7. Okay? Just do it for yourself with r equals negative 3/7 and make sure you follow how that works. Okay? Awesome. So this fact that these limits are always 0 are huge. What else? Something to make you feel better, maybe. Proof won't be on your quiz. It probably will be on your test, but won't be on your quiz, okay? So that may help you breathe a little bit easier. So we've just proven this guy. I'll stand back one more time so you got it, and then you can pause wherever you need to. And let's just make a quick assessment here of this particular sequence, r to the n. Right? So for the sequence, r to the n, what do we have, right? This guy, r sub n converges to 0, right, as n goes to infinity, for what? Really negative 1 less than r less than 1, right? Because it's also 0 when r is 0, right? So it goes to 0. So we got converge, converge, converge here, right? Okay, converge, converge, converge. Converge, 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 and converges to 0. To 0, to 0, to 0, right? What if r is 1, right? Okay, So if r is 1, right, then 1 to the n, that's this sequence. Well, that goes to 1, right, as n goes to infinity, right? Because this sequence is just 1, 1, 1, 1, 1, 1, 1, 1, 1, right? It doesn't change, right? So here we have converge, and it goes to 1, right? Okay. Then what else? What if we have the sequence, what if r is negative 1? This is the guy we already talked about last time. Does that guy converge? No, this guy diverges, right? Why? Because it bounces back and forth between negative 1 and 1, right? So at negative 1 we diverge, yeah, diverge. And then for this sequence, right, so this is all for the sequence r to the k, r to the n. And then finally what's left, right? What if r is bigger than 1? Okay, if r is bigger than 1, then, well, you can think about it. It makes a lot of sense. If r is bigger than 1, like 2, 3, and we're taking the limit as n goes to infinity of 2 to the n, 3 to the n, right? 4 to the n, all of that kind of stuff, right? What's going to happen out here, right? Out here is all diverge, right? Okay, it's going to go off to infinity, right? Grow positive without bound, and so we diverge, goes off to positive infinity. And if r is less than negative 1, right? If r is less than negative 1, if I'm a number down here, like negative 2, negative 3, right? Negative 2 to the n, negative 3 to the n. Well, then I'm growing unbounded, but growing unbounded by bouncing back and forth between numbers that can consistently get bigger and bigger, positive and negative, right? Okay, and so out here we have diverge as well, and it just does not exist. It's not going off to positive or negative infinity, just bouncing back and forth between numbers that both grow large without bound. Does that make sense? Okay? And so here we got diverge. Right, does not exist. This also doesn't exist, but it gives you more information, right? Does that make sense? Okay, and so that's everything, right? Okay, so this is r equals 1, and this is r equals negative 1, and there's also visuals of those guys. And this is minus 1, less than r, less than 1, right? Visuals of those in your book as well. Okay, that sequence will, ideas related to that sequence will be coming back around. For fun, you could try to prove this one, right? Try to prove that one using our proof definition. Maybe pick your favorite r, bigger than 1, or just pick a specific r, right? So, prove the limit as n goes to infinity of 2 to the n goes off. So here I'm picking r equals 2, right? Goes off to infinity, right? Or if you're feeling, dangerous here, get general, prove the limit as n goes to infinity of r to the n goes to infinity for r greater than 1. Okay? Use the definitions of what it means for this guy to grow large without bound. Okay, that's our n in our m definitions, right? There's no epsilon in those guys because you can't get close to infinity, right? That one says that for every m greater than 0, there exists a capital N greater than 0, such that if little n is bigger than capital N, then 2 to the n is bigger than m, right? I can make this guy bigger than any other guy you give me, yeah? Right? That's what it means to grow large without bound. Okay, so now what? Now we're at our final piece of the puzzle for section 11.1. So let me grab a drink again of water and erase this and do our last little bit. Alrighty. so what's left? A few definitions, some more terminology, and one more awesome theorem, okay? So now we're in the more terminology section, okay? These all obviously weren't in order. So more ways to describe sequences. We want some more words, some more adjectives, more vocab words, right? We want to expand our vocabulary, right? That's our goal, okay? We don't want to be just stuck with, our simple, well, not at all simple stuff that we've already talked about, right? We want to expand our vocabulary. So let's do that. We can say that a sequence is increasing. Oh, that word sounds a little familiar, like calculus, right? If what? Okay, so what would that mean, right? So let's think about, again, what does this thing mean when you see this? This is shorthand for a set of infinitely many numbers listed in order, A1, A2, A3, right? A4, on and on forever, right? There's an AN, and then there's always a next term, AN plus 1, right? And then it just keeps on going, right? Does that make sense, right? This guy's AN plus 1, right? No matter what two pairs you pick. Okay, so a sequence is increasing. What would that mean, right? It would mean that as you move left to right, the numbers would get bigger, yeah? Okay, so how do we say that in math terms? If I move left to right, the numbers get bigger. So you guys tell me, this sequence is increasing if, good, AN, we're going to say it in general, is less than AN plus 1. Or AN plus 1 is bigger than AN. I kind of like it that way because it kind of has the increase piece. But we'll just go with it this way, right? Does that make sense? Right? This guy, the next guy is bigger than the previous guy, right? All right? And that's for all n greater than or equal to 1. That would mean the whole sequence is increasing. Sometimes you can just be like, okay, well, it doesn't matter. Somewhere down the road, maybe after A4, the sequence is increasing, right? And so that's called eventually increasing, but we're not going to worry so much about that. Okay, so that's increasing. So what do you think the definition then for decreasing is? Okay, and a sequence is decreasing if what? Well, what would decreasing mean? The previous term is bigger than the next term, right? Okay, the previous term is bigger than the next term. So in general, A sub n is bigger than A sub n plus 1, right? Yeah, we got it. Same idea. For all n greater than or equal to 1, right? Similarly, a sequence could, bounce around at first for a little bit and then eventually settle into constantly decreasing, okay? All right. I'm gonna write down these examples. I'm gonna write down one more thing, and then we're gonna look at an example. There's one more word. We say that a monotonic sequence. We call a sequence monotonic if it only does one of those things. If it doesn't go up and down, right? Okay, so it's just like a monotonic increasing function like e to the x, or monotonic increasing function, natural log, which we just talked about. Same idea, monotonic sequence. E to the negative x, monotonic decreasing, it's still monotonic, right? Only going in one direction. So a monotonic sequence either only increases or only decreases. Not both, right? Yeah? Okay. Only increases or only decreases. Yeah? Okay, so your book does an example, and I want to do of looking at testing. There's a couple of examples of testing sequences with these conditions for increasing and decreasing. So I want to do a slightly different version. Example 12 is, let's see, let's look at example 12, which is the sequence 3 over n plus 5. Okay, so read the book's solution of example 12, 3 over n plus 5, using these guys to decide whether the sequence is increasing or decreasing, right? But we're going to take a different tactic and think about what happens when we try to invoke some calculus too. So another option, and before I say this, I just want to again say, the things that we do here are important as well. Make sure you understand what the book is doing in these guys. We'll see those a little bit more later, so as applied to example 12. In example 13, they do things both ways, and so I want to just give you the both ways version of example 12, okay? So remember what we know about calculus, right? So what if we said, like, so calculus, right, for functions, calc 1, right, we said f is increasing if what? Good. The derivative, the slope of the tangent line, right, is positive, right? Okay? And what did we say about f is decreasing if, here we have a continuous function where these guys are just a bunch of numbers, right? It's just a bunch of dots, not functions. So we can't take derivatives of dots, right? Okay? But f is decreasing if f prime is negative. Good. Slope of the tangent line is negative. Good. Okay, so we can exploit these ideas though, because this guy, right, he's our a sub n, right? But we can say, okay, well, what if I created a function f of n, right, and thought of this as a function of natural numbers, so this is still discrete, right, it's still a bunch of dots, and so I called f of n 3 over n plus 5, right? Then I could look at the continuous version of that guy, f of x, where x is a real number, just like we did when we went and did L'Hopital's rule, right? You know, L'Hopital's rule applies to continuous functions, so you can't really do L'Hopital's rule with n's, right? It's not really legit, even though lots of people do it that way just because you're just using it for a symbol. But anyway, 3 over x plus 5, right? Yeah? So if this is f of n, then this is f of x. Put an x everywhere you saw an n. Yeah? Good. All right, well, so can we utilize this idea, okay? Well, is this a function that's easy to take the derivative of? Well, yes, indeed. How would you take this derivative? Now, some of you may have said quotient rule, which is quite, true because it's written as a quotient. Written this way, you have to use quotient rule, but quotient rule is uglier, and you'll often mess it up because, despite how many times we try to beat that through your heads, we still get people who swap the sides, and okay. Anyway, so in order to avoid quotient rule, how would we have to write this function? Good. 3 times x plus 5 to the what? Negative 1 power. Excellent. Try not to fall down the stairs here. That could be an interesting end to the video. Okay, so f of x is 3 times the quantity x plus 5 to the negative 1. So therefore, what is f prime of x? 3 is a constant, right? The constant multiple rule for derivative says the derivative of a constant times a function is the constant times the derivative of the function, right? This function is stuffed to the negative 1. What's the derivative of stuffed to the negative 1? Bring down the power. Do what with the stuff? Good. Leave the stuff alone. Don't touch the stuff. Then do what with this power? Subtract 1. Nice. And then multiply by the derivative of the stuff. What's the derivative of x plus 5? Good. 1. Very nice. So what is f prime? Let's rewrite it. Okay. I got 3 times negative 1 times 1. That's negative 3. This negative exponent, let's throw it down to the denominator. So I got f prime of x is negative 3 over x plus 5 quantity squared. Yes? What can you tell me about the numerator? The numerator is always negative, negative 3. What can you tell me about the denominator? Stuff squared. Stuff squared is always positive. Negative divided by positive is always negative. This derivative is always negative. And if the derivative is always negative, then the the function of a continuous variable is always decreasing, and one of the nice things about our work with sequences is we can now exploit that with the ideas that are in section 11.1 to say that this is another way to test the sequence. The sequence itself also has to decrease, okay? Because that sequence is just going to be a series of dots along that curve, right? And that's also going to decrease. And so that is another way to show that this example 12 is a decreasing sequence, okay? Does that make sense? So look at the book solution for example 12 utilizing this guide, and then example 13 does a different sequence and does it both ways, once with calculus and once with these definitions. Yeah? All right. Final piece of the puzzle, okay? Final piece of the puzzle is an awesome theorem, okay? Oh, whoops, I forgot 2 more definitions. So 2 more definitions and then an awesome theorem. Okay, so 2 more definitions and then an awesome theorem. Here we go. I'll just keep going here. I should probably use this stool and maybe my husband bring it up, so I'll use it. Okay, so let's see. Our next definition, another vocab word for sequences, is that we say that a sequence is bounded above. Okay, a sequence is bounded above. Oh, I'm not going to be able to use that so very long. If what? If there's some number, if there exists some number, okay, we'll call it, I'll use the book's notation, which is capital M, but don't confuse that with the other capital M from our limit definition. If there exists a capital M, such that, let's write this down and make sure we see what it says, right? Such that the nth term, right, any term, is smaller than or equal to capital M, right? So this guy is an upper bound. It's a number that is bigger than or equal to every number that's in the sequence, right? Does that make sense? Every number that's in the sequence. Okay. And again, so we should say for all n greater than or equal to 1. That's the definition of bounded above. Okay, so what definition is coming next? Good. Bounded below. You got it. A sequence is bounded below. You could finish this without me even, right? If what? There's got to be some number, using the book's notation, little m, that makes a lot of sense, right? Little m is going to be what kind of a bound? Good, lower bound. Okay, a lower bound. Such that what is true, right? Well, if this guy's a lower bound, then it's smaller than every number in the sequence, right? Smaller than every number in the sequence. So what would we write? If we keep this same notation, a sub n is greater than or equal to little m, or little m is less than or equal to each a sub n, right? Okay? For all, again, n greater than or equal to 1, right? Bounded above and bounded below, okay? Okay. Just write that here. Bigger or equal to each term in the sequence, right? And this guy is smaller or equal to each term in sequence. Yeah? And why do we need to know those, I need to know those 2 things, because that brings us to our last topic in this section. Again, a lot of these things are going to start getting used a little bit later, so just, hang tight. It's in my way now with school. Okay, just hang tight. But here's our awesome theorem. Okay. Now this theorem gets all kinds of use in some later math classes, but it's also going to help us out in a variety of places as well. So here's the awesome theorem. If, we'll write it this way, if a sequence, right? So when you see these curly braces, you think sequence. It's a set of infinitely many numbers, ordered, right? A1, A2, A3, blah, 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 right? Okay. If a sequence is bounded, so that means either bounded above or bounded below. We don't care, okay? Oh, sorry. Yes. We're good. Okay, yes. And monotonic, okay? If it's bounded and monotonic, right, then what? And the sequence converges. We got convergence, okay? We've got convergence. We don't know what the limit is. Don't know the limit. You don't know L. But you do know convergence. Right? You don't know L, but you do know convergence. All right. Your book states this as theorem 12, okay, in your book. It states this as every bounded monotonic sequence converges, right? This is an if-then statement of that same thing. Every bounded monotonic sequence converges. If the sequence is bounded and monotonic, then it must converge. So sometimes you don't really want to know the limit. You just want to know whether or not the sequence converged. And if it's, this theorem tells us if it's bounded and monotonic, then it will converge. I think I'm probably a little bit slower than I wanted to be. So maybe we'll stop here, and I'm gonna hopefully do a little intro into section 11.2, depending on how long this video is, so that we can kind of get the difference between a sequence and a series, which is coming in the next section. All right, all for now. Have a good, whatever it is, whenever you're watching this video, have a good evening, morning, afternoon, and I will see you online again soon.